Okay, let's start now. Can you hear the microphone at the back? Can you hear the microphone? Okay, so we're going to do some examples of solving systems of linear equations. So here's the first one. We've got this system of three linear equations in the unknowns x, y, and z. So now we want to reduce to row echelon form. Okay, so this is Gauss reduction. And the first step is to write down the augmented matrix of the system. So we could continue to write down x, y, and z all the time, but we're doing this to save time so that we don't keep writing down x, y, and z. So this first column is the coefficients of x. The second column is the coefficients of y. Third column, z, and then on the right-hand side. Okay, so our first goal is we want to get these zeros in the first column. So that's what we want to do first. We want to have, so when I write a star, it means it could be anything. It's not important what that is. What is important, we want these zeros here. Okay, so what we could do is we could say row 2 minus half row 1. And then we'll get this zero here. If we do row 2 minus half row 1. But then we're going to have fractions because we've got to do the same operation across the row. And then we're going to have fractions, and we don't want to have the fractions unless we can avoid it. So the first thing we're going to do is before we try and get these zeros here, is we swap row 1 and row 2. Because now we've got a 1 there, and it's much easier to do row 2 minus 2 row 1. Now if we do row 2 minus 2 row 1, there won't be any fractions. Okay, so we want to get a 0 here and a 0 there. So the first step of switching the rows was just to avoid having fractions. Okay, so that's why we did row 1 and row 2. So now we're doing row 2 minus 2 row 1 to get that 0 there. Row 2 minus 2 row 1. So now we've got that 0. Then we're doing another operation at the same time. We want to get a 0 here. So we can get that just by subtracting row 3 minus row 1. And then we've got this 0 as well. Okay, now you have to watch out and be careful because we've done two operations at once. So we did two operations at once. And that is okay. If we would get the same result if we did them one after the other. Doing them in 2 steps. Okay, so this is one of the ways we can go wrong with these row operations. We can do 2 steps at once, which couldn't have been done with the same result doing two steps one after the other. Now you can see why we can do these 2 steps together, because now in the first one we've changed row 2. In the first step here, row 2 minus 2 row 1, we've changed row 2. Now in the next step that we're doing at the same time, we are using rows 3 and rows 1. Row 3 minus row 1. We are not using the row that got changed. We're not using row 2. So it's all right to do them both at the same time. Okay. Now we've got to this step here. What do we want to do next? So the next thing we want to do is get a 0 over here as well. Okay, and we've got the stuff on the right-hand side, which we're also not worried about. Okay, so that's what we want to do next. So if we row reduce to row echelon form, that means every row must start with more zeros than the one before. Okay, not very legible. Is everyone happy with that? Every row starts with more zeros than the one before. Okay, so here you can see, okay, row 1, there's nothing before row 1. Row 2 starts with more zeros than row 1. And we want row 3 to start with more zeros than row 2. Okay, so our next goal is we want to get this 0 over here. So we want a 0 over here. Now we've got to be careful. We don't want to get this 0 and at the same time spoil this 0 entry over here. We want to keep this 0 entry. So about the only thing we can do, we don't want to use row 1 because then we'll spoil this 0 entry. So we've got to use row 2. So we're doing row 2 minus row 3 to get this 0 here. We can do row 2 minus row 3. Okay. So that's what we do with the row reduction. And we've now row reduced to row echelon form. And this is Gauss reduction. Now you can reduce further and do Gauss-Jordan reduction. But we're not going to do that now. We're just going to stop here for the time being. And now we are ready to solve the system. So now we can solve the system from the bottom up. So once we've got our system in echelon form, okay, now we've got our system in row echelon form. Every row starts with more zeros than the one before. Now we're ready to solve from the bottom up. So we start with this row. And it immediately says Z is equal to 1. So we've got Z. We're going from the bottom up. So Z is equal to 1. Now we look at the next row, which says y is equal to 1 minus 2z, taking it over to the right-hand side. Y is 1 minus 2z, and that means that y is minus 1. Okay, and then we go all the way up to the next row. Now we can get x. So we take everything over to the right-hand side. X is 1 minus 2y minus z. Okay, the 2y and the z are going over. And we know y and z, so we've got x now. X is 2. So we've got a unique solution. We've got a unique solution, x, y, z. And we can write our solution in a vector form like that. Okay, so we can write our solution like that. Now if you want to be sure that this is right, what you have to do is go back to the original system. Yeah, go back to the original system and check that these values for x, y, and z are actually solutions of the original system. You can check it, okay? X is 2, y is minus 1, z is 1. Substitute into the original system and make sure that all these equations are satisfied. Then you know that your answer is right. Okay, so that's an example where we've got a unique solution. Are there any questions about this one? So there's a unique solution. Okay, so here's a system which has got no solutions. So we start out again with these three equations in x, y, and z, and we write down the augmented matrix. Okay, is everybody happy with this? You write down the augmented matrix. Now we're going to solve it in exactly the same way as we solved the first system. Now we are happy with the one there. So what we want to do is again we want to get 0, 0. So this is what we're aiming at again, as in the first example. So how do we get this 0? We can take row 2 minus row 1. How do we get this 0? We can take row 3 minus 2, row 1. Okay, so we do that. And now we've got a row of zeros. So then you have to think a bit, what does this row of zeros mean? So what happened was that the 1, 2, 1 was double 2, 4. Doubling 1, 2, 1, you get 2, 4, 2. So we got a row of zeros. So now if you look at this set, the third row, and if you think what does it mean as an equation? So it means 0x plus 0y plus 0z is equal to 1. If we interpret back what does it mean as an equation? So it says 0 equals 1, which is not true. So our system of equations has led to a contradiction, 0 equals 1. that means our system of equations doesn't have any solutions. If it has got solutions x, y, and z, then 0 is equal to 1. So it has no solutions. Okay, is that clear? So if you have a row of zeros on the left and a non-zero thing on the right, like we have here, then it means, if you think of it as an equation, it means 0 equals something which is not 0, and that's not true, so we can't have any solutions. Okay, so there are no solutions. Okay, so here's another one. So here's another system of equations. And we write down the augmented matrix. Okay, so once again, we want to have okay, so we're aiming at this system here. So we can do row 2 minus row 1, and we'll get this 0 here. And we can do row 3 minus 2 row 1, and we'll get that 0 there. So I should say again, once again, we've done 2 operations at once. So again, we should be careful when we do 2 operations at once that you would get the same result if you do them in 2 steps, one after the other. And you can see that there's not a problem here because as in the 2 previous examples, this step, row 2 minus row 1, changes row 2. Here we changed row 2. But our next operation doesn't use row 2. It only uses row 1 and row 3, which haven't been changed in the first step. So it's all right to do 2 steps at once. And now what has happened is we've got a row of zeros. Complete, so we've got now 0, 0, 0, and we've got 0 on the right-hand side. So this equation says 0x plus 0y 0z equals 0, which says that 0 equals 0. So that equation is giving us no information. It's just telling us 0 equals 0, which we already know. So this is no information. And we can delete this row. Okay, so we're not going to write that row. Now we've only got 2 rows. 1, 2, 1. This one, the first 2 rows are the same as before. Okay, now have we finished doing the row reduction? So every row starts with more zeros than the one before. Is that true? So the first row, there's nothing before the first row, so it means nothing. The second row starts with 1 0, and the row before the first row didn't start with any zeros. So this is now in row echelon form. So our system is in row echelon form. We've finished the Gauss reduction. So you can continue further and do more row operations and get Gauss-Jordan reduction, but we are now ready to read off the solutions. So we're going to do it from the bottom up. Okay, but now I must also explain the leading entries. So how do we read off the solution when there are many solutions? So we've got the leading entries are the first non-zero entry in its row. Okay, so I've circled the leading entries. This is the first non-zero entry in row 1. And here's the first non-zero entry in row 2. We've circled the leading entries. Now, every column corresponds to one of the variables x, y, or z. So the first column, these are all coefficients of x. The second column, these are all coefficients of y. And the third column, coefficients of z. Okay, so the leading variables has its leading variable, so its column of coefficients contains a leading entry. Okay, so that's what a leading variable is. Okay. So we've got two leading entries. So the leading variables, look at the coefficients that are in the column of our first leading entry, that's x. The second leading entry is in the second column, and that's the y column. So x and y are leading variables. And the free variables are the other variables. So Z is the free variable. Okay, so this is important for the solution because now we give the free variable arbitrary values. Okay, so we give the free variable z an arbitrary value. So that means we've got z equals t. Okay, so z can be any real number. And then we solve for the leading variables from the bottom up. Okay, so we must, we've got three unknowns and we've only got two equations. So there's going to be a free variable. So what is a free variable? First, you've got to identify the leading entries. So you must have reduced your system to row echelon form. Then you can identify the leading entries, and every column corresponds to a variable, and the columns which contain the leading entries show you the leading variables, which are x and y. Now, a variable which is not a leading variable is called a free variable, and the way you solve the system is you give the free variable there could be more than one free variable, but in this case it's only one. So we give the free variable an arbitrary value. It could be anything. So we'll say it's t, any real number, and now we solve from the bottom up. Okay, so we're going to use the first equation, the last equation here. We're going to use the last equation to get y. So z is t. If you look at the last equation, it tells you y plus t equals 1. So y is 1 minus t. And now we want to get x, so we go up to the next equation. We've got x is 1, so x is going to be 1 minus t, minus 2y. And then we substitute for y, because we know y is 1 minus t. And then we can solve and we get x is minus 1 plus t. Okay, so we give the free variable an arbitrary value, and then the leading variables we solve, as we always do in row echelon form. We always solve from the bottom up, Okay, and we can write our solutions in a vector form. So our solution x, y, and z, there's a constant, and there's a multiple of t. So x is minus 1 plus t. Y is 1 minus t, 1 minus t. And z is t. So we can write it can write our solutions in vector form. Okay, so what I could do is try and say something about the Gauss-Jordan form. So once you've finished reducing to row echelon form, you can still continue your reduction to Gauss-Jordan form. I'm not sure if I really want to do that. Okay, so with the Gauss-Jordan form, why do you do it? So for solving equations, when you're solving equations, you do some more row operations, which is extra work, but hopefully you save on the extra work by being able to read off the solution more quickly. So shall we just continue and do continue this example and just do one more step, and it'll be in Gauss-Jordan form. Okay, so I'm just going to do the one that we've just done. So it's in row echelon form, but we can do another step to put it in the Gauss-Jordan form. Okay, so we'll do one more step. Okay, so if you look at the leading entries, in Gauss-Jordan form, So let me just explain what the Gauss-Jordan form is. Okay, so there are two things. Firstly, the leading entries must be 1. Which we've got here. I've circled the leading entries. They are 1. And secondly, the leading entries Okay, so if you have a leading entry, it must be a 1. So we've got that, 1s. And also, if you look at a column which contains a leading entry, the leading entry must be the only non-zero entry in that column. So here's a column containing this leading entry, and the leading entry is the only non-zero entry in that column. Okay, but now look at this leading entry here. It is not the only non-zero entry in its column, and because of this 2 here. So we want to make the 2 a 0. Okay, so another thing I should say is that when you do the Gauss-Jordan form, you should work from right to left. Right, so what can we do to get a 0 here? And if we use now, we are looking at this column first. This one is already okay, so we want to get a 0 there. So all we do is we take row 2, row 1 minus 2, row 2. Then we'll get a 0 there. Row 1 minus 2, row 2. Okay. So what was the point of doing that? And now you can see it's in Gauss-Jordan form because we've got these leading entries, and every leading entry is the only non-zero entry in its row, in its column. Okay, this leading entry, the other entry in this column is 0. Same. Okay, so what was the point of doing this? Well, now we can read off the solutions a bit more easily, because we've got one free variable z. We've still got the one free variable z. So z is t. Now we solve for y. Y is 1 minus t. And then we want to solve for x, and it's a little bit easier to solve for x because there's a 0 over here. So we can see x is minus 1 plus t. Okay, so we do a bit of extra work doing this row operation. but then it's easier to read off the solutions. Okay, so I think I'm going to stop there.